Hello, my name is Ferit Bilgi. I am a computer science student and today I will walk you through overview of my experimental investigation of the capacitance formula using an adjustable parallel plate capacitor. First, what is a capacitor? A capacitor is a passive electrical component that stores energy in the form of an electric field. In its simplest form, it consists of two conductive plates separated by an insulating medium. When a voltage is applied, equal and opposite charges accumulate on the facing surfaces of the plates, and the amount of charge stored per volt is defined as the capacitance C. In our experiment, we used a custom adjustable parallel plate capacitor apparatus. Each plate was a circular aluminum disc with a radius of 9 cm, mounted on a precision track that allowed us to vary the plate separation from a few millimeters up to over a centimeter while maintaining parallel alignment. To measure capacitance, we connected the plates to a high-resolution LCR meter capable of detecting values in the pico-2 nanofarad range. We also had a caliper for measuring plate separation and various thin dielectric sheets, wood, glass, and paper with known dielectric constants. The experiment was carried out in three parts. 1. Capacitance versus plate separation. We held the overlapping area, full 9 cm radius discs, and recorded capacitance at separations of 2 mm, 4 mm, 6 mm, 8 mm, 10 mm, and 12 mm. As predicted by ideal formula, C equals epsilon 0 A over D, capacitance decreased roughly inversely with distance. When plotted against 1 over D, the data formed a straight line, confirming the inverse relationship. The second part is capacitance versus overlapping area. Keeping the separation fixed at 5 mm, we shifted one plate laterally to achieve 100%, 75%, 50%, and 25% overlap. The measured capacitance scaled almost linearly with overlap fraction, demonstrating that C proportional A. The last part is the electric effect. With the full overlap and 5 mm separation, we measured the baseline capacitance, then inserted each dielectric sheet in full contact between the plates. Materials with higher dielectric constants produced proportionally higher capacitance. For example, paper increased capacitance by a factor very close to 2.77 compared to the air. Throughout, we noted non-ideal effects. Fringe fields at the plate edges caused measured values to exceed the ideal prediction by up to 10%, particularly at larger separations. We minimized this by using large plates relative to the gap and by subtracting stray capacitance from our readings. In conclusion, our results validate the core principles of the parallel plate capacitor. Capacitance is directly proportional to plate area, inversely proportional to plate separation, and scales with the dielectric constant of the material between the plates. By using 9 cm radius adjustable plates, we were able to explore these relationships experimentally and observe both ideal behavior and real-world deviations. Thank you for watching.